So in the second part of this, we're going to talk about measurement and measurement technique. So one of the things that we fundamentally need to realize is that all measurements in the end are approximations. At some point, it's going to get to where my eyes or my computer really can't tell the difference between markings or values on a piece of equipment. So all measurements are going to involve a certain amount of uncertainty. We're going to get to a point where we can't read it anymore. So that means all measurements are going to depend on two factors. They're going to depend on the measuring instrument. No instrument is absolutely accurate. And it's also going to depend on the skill of the person using that equipment. Because even if my equipment is perfectly wonderfully accurate, if I don't use it correctly, then I'm not going to get all of the information I can out of it. So no instrument is absolutely accurate, and no operator is going to be absolutely precise. Well, those are two words that we probably want to make sure we define. What does it mean to be accurate? What does it mean to be precise? So what is the difference between those two numbers? It seems like they ought to be fairly similar. Well, not really. Accuracy versus precision. I think the easiest way to talk about it is to talk about it kind of in terms of the metaphor of trying to do archery or playing darts. Accuracy in a measurement is how close that measurement is to the accepted right value. So you kind of summed it up here in this box. If a measurement is accurate, it is correct. Precision is something that we're actually going to really need a series of measurements. You really can't say one measurement is precise. But if we have a series of measurements, then if those measurements are very close to each other, if I measure it again and again and again, and I get consistent results, then I would say that the measuring equipment is precise and my ability to use it is precise. As I read it, I'm reading the same number for the same object over and over. So if we think about this in terms of archery, let's look at a couple of situations. This would be me doing archery because I don't know how to shoot a bow and arrow at all. So if I did it, I would be lucky if I even hit the target. But let's say I have this situation. I've shot 3 arrows. Now, where do I want to be if my arrows are accurate? Well, if my shots are accurate, then I'm going to want them all to be in the bullseye, right? That's what we want when we're doing archery. So really, only one of these arrows is even close. So I don't think that this is a very accurate reading. So precision, remember, is about agreement. So if I'm looking at whether these arrows agree with each other, well, one is on the edge between the bullseye and the white ring, one is all the way out in the yellow, and one is out in the blue. So they aren't really agreeing with each other either. The arrows aren't close to each other, and they're not in the bullseye. So they're not very right, so they're not very accurate, and they're not very much in agreement. So this is the worst case scenario. In this case, it is neither accurate nor precise. So let's look at another situation. What do you think about this one? So in this case, well, if accuracy is about hitting the bullseye, this is someone who's still not quite on. They're not hitting the bullseye with these arrows. So I really don't think they're very accurate. But all of those arrows ended up very close to each other. So each shot gave me a very similar result. So in this case, my arrows are close to each other. They're reading the same over and over, but they're not landing in the bullseye. So maybe my archer needs to learn better how to correct for distance or wind. It is actually quite possible to be precise, but to not be very accurate at all. So here's our last one. This looks nice. So this is a person who has hit the target. That's the correct place for those arrows to end up. And all of those arrows have hit the target. So they are close to each other and they're in the bullseye. So they're in great agreement and they're right where I want them to be, in the right spot. This would be the best case scenario. In this case, this archer is both precise and accurate. In order to do that, we need to pay attention to calibrating our equipment. Calibration is going to improve accuracy, and it should also, in the end, improve our precision as well. If an instrument is well calibrated, it should agree with itself when I measure the same object. So in a calibration, we're going to take the instrument and we're going to take a standard known object. We're going to measure that standard known object, and we're going to make sure that the instrument reads what that known object is. So let's say this is something we do with balances a lot. If I put a 1 gram standard mass on a balance, then if that balance does not read 1 gram, that tells me I need to calibrate or adjust that balance so that it does say that this 1 gram standard, this known to be 1 gram object, reads as exactly 1 gram. Now my reading is accurate. It is agreeing with the accepted or standard value. What would happen if I put a 1 gram object on my balance, and instead of saying that it reads 1 gram, it would actually read 1.5 grams? What would happen to our readings? I think the easiest way to think about this is just to think about it in terms of doing a little bit of math. Every 1 gram instead reads 1.5. So if I put 2 objects on there, then instead of it reading 2 grams, it would read twice 1.5. So instead of reading 2 grams, it would now read 1.5 times 2. That would read 3 grams. And we could make this go up even more. Let's say I take 10 of those standard objects. Where it would supposed to be, that 10 of those standard objects reads exactly 10 grams. But now I have 1.5 plus 1.5 plus 1.5 plus, oh wait, I don't need to do that. That's what multiplying is for. I have 10 1.5s. That means instead of reading the correct 10 grams, it would read 15 grams. So every time now, our readings are ending up too large because our calibration is off. This would be a case where we could be very precise. It could read, say, 15 grams over and over and over and over and over, but it's not accurate because the actual mass on the balance would only be 10 grams. So those readings would all be too large in this case. Since no measurement is on a perfect instrument and no person is perfect, we are always going to have an amount of uncertainty in any measurement. So let's think about what happens there. Where is that uncertainty? We want our best accuracy, and that means that we're going to have to read everything we know on our instrument using the marks or graduations on our instrument. But the part that people often forget to do is to get a little bit more information by estimating between the marks on the instrument scale. So if I look at this instrument, since we generally use metric units in science, I'm going to pay attention to the centimeters part. Each one of the large graduations with the number is 1 centimeter, but there are smaller graduations in between the centimeters. I can see there's one middle size graduation that's halfway in between each of the larger numbers. And if I look at this, my graduations are 1, 2, 3, 4, 5. So that's actually tenths of a centimeter because it's 6, 7, 8, 9, 10. That's the next number. So let's take an object and put it up next to this. So what I can tell you often happens with an object like this is I will have a student tell me that this object is about 4.4 centimeters. But remember, you've forgotten to do the important last bit. You have not estimated between the marks on the instrument. So I'm going to record everything I can get for my graduations plus that one estimated digit. When I do that, I find if I draw this line here, I know that it's bigger than 4. I know that it's bigger than 4.4. And when I have to start estimating between those lines, I can see that it looks like it's about halfway in between the 0.4 and 0.5 lines. So I could call that 4.45. But reasonable people can look at that object and they can disagree about whether it is exactly halfway between the 0.4 and 0.5 lines. You might think that it's a little more than halfway. So you might say, well, I know it's bigger than 4 and it's bigger than 0.4, but I think it's actually closer to 4.47 centimeters long. And so that is that estimated or doubtful digit. It's really easy to find that in a measurement. It's always the last number. That's where we have to stop reading lines or graduations and start doing the estimating. So we're going to come back and talk about this a lot. This is the concept of a significant digit. And we'll talk about rules and determining significant digits coming up. So let's practice this a little bit. Okay, let's look at the volume of the liquid in this 100 milliliter graduated cylinder. So I know in the end, the last part of my measurement is going to be the unit, that is in milliliters. So I'm going to get down eye level to this graduated cylinder. And I'm going to look, remember, at the bottom of that U shape or the meniscus, because the bottom of the meniscus is always where we measure. So the first thing I'm going to do is I'm going to look at what are the graduations, the measurement lines on this equipment. So of course I see the big 60 and the 70. So now I want to look at in between 60 and 70, how many lines do I see? I see 1, 2, 3, 4, 5, 6, 7, 8, 9 lines, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. So in between 60 and 70, I would see that being 61, 62, 63, 64, 65, so on. So those are graduated in 1 milliliter increments. So if I look at this, it's definitely bigger than 60. It's definitely bigger than 61. It's definitely bigger than 62. So since these are 1 mil graduations, I can say that this is at least 62 milliliters. But I don't want to stop there because I've missed that last step. I can always estimate between the lines to get myself a little better information. So now if I look at that orange line, and I remember that I always need to estimate between graduations, now I don't know exactly where it is between 62 and 63. That's my estimate, my doubtful digit. But if I look closely at that, it looks like it's a little more than half. So I might estimate that at, say, 62.8 milliliters. Because if I divide that graduation up into equal pieces, I would be in the 0.1 place. So I would estimate that as 62.8. But could a reasonable person absolutely think that that's 62.7 or 62.9? Absolutely. That's why it's the estimated or doubtful digit. There's no question it's bigger than 62 and less than 63. But that estimated decimal place is going to be where our uncertainty lies. Let's try another example. Instead of using a 100 ml graduated cylinder, let's do a 10 ml graduated cylinder. So the first thing I have to think about is, what is the line? What are the graduations here? So now, in between 6 milliliters and 7 milliliters, I have a bunch of lines. And so I'm going to see I have 1, 2, 3, 4, 5, 6, 7, 8, 9 lines again, which means I'm dividing this up into 10 equal pieces. That means in between 6 and 7, I have tenths. I have 0.1 of a milliliter. So I'm going to look at it and I'm going to see first, I definitely know it is between 6 and 7. So I have at least 6 milliliters. And now I'm going to look at the bottom of that meniscus, and I'm going to look at that yellow or orange line, and I'm going to say, well, it looks like that orange line is, if I estimate between my graduations, it looks like it's pretty much right on 6.5. But I don't want to write down just 6.5 because I can always estimate between my graduations. And if I just write down 6.5, I haven't given myself credit for my good technique of really looking and saying, hey, that is right on that line. So I would divide 0.1 graduations into a 0.01 increment. So in order to give myself credit for my good measurement technique of looking to see that it is exactly on the line and I can't estimate any more between them, I would write down 6.50, not just 6.5. And it's certainly possible that a reasonable person could look at that meniscus and see it as being just a teeny little smidge above the 6.5 line. And they might say, hey, I think that's really closer to 6.51. That's why it's my doubtful estimated digit. So last thing we're going to do is we're going to look at something that you see on pieces of equipment. Oftentimes you'll see that you have a value plus or minus something. And that is a measure of the uncertainty in the measurement lines. So say, for example, I have a centigram balance, which often has an uncertainty of plus or minus 0.02. So what that tells me is no matter how closely my balance is trying to measure that amount, it means it can't tell the difference any closer than 0.02. So my real reading here, since it's not a perfect instrument, if it reads 32.00, my real number is actually in between. It could be as big as 32.02. My instrument can't tell the difference between 32 and 32.02. Or it could be as small as 31.98. But it's definitely in between those two numbers. So really, plus or minus is as easy as following the instructions on the mathematical symbol. I take my reading and I add the number for the plus, and I subtract the number for the minus. And so the biggest possible reading would be the reading plus that. The smallest possible value would be the reading minus that. So this is a pretty good balance. The error in that reading is very, very small. But if I do several measurements and say I get 31.99, 32.00, 32.01, I really can't say that those are significantly different from each other because they're all in that in between that plus or minus reading. I can't say that my instrument is accurate and precise enough to tell me exactly that those readings are significantly different. So here are some practice questions to think about. Give an example of a count for people. And also give an example of a measurement of a person. And I want you to think about what determines the accuracy of a measurement. And give me an example of a situation where we really need to use those standard units.